what really happened during the Ordovician. Today, we're going to explore a vast, submerged, and still untouched world where life, having awakened, begins to diversify in all directions. A world without forests, without terrestrial predators, without birds in the sky, but populated by countless strange and abundant marine creatures. Welcome to the Ordovician, the golden age of the seas. More than 470 million years ago, Earth was an archipelago of barren continents, and the shallow oceans were the vibrant heart of all life. Trilobites crawled over the seabeds, brachiopods anchored to rocks, and sponges, primitive corals, and algae intertwined in vast, developing reefs. But before heading out on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and enjoy the journey. The Tremadocian, from 485.4 to 477.7 million years ago, is the first subdivision of the Ordovician. Inheriting from the Cambrian, it marks a major ecological adjustment, with a gradual resurgence in the diversity of life. This post-Cambrian revival period saw new marine organisms exploiting niches left by Cambrian extinctions. Shallow or epicontinental seas became the stage for these evolutions, offering ample space for expanding species. The Tremadocian is distinguished by the presence of phosphatized microshells, remnants of primitive mollusks and worms, indicating the creature's adaptation to protect themselves from predators. Graptolites, notably in dendroid form, developed abundantly. These colonial organisms, forming tubular structures of collagen, are well preserved in sediments and became valuable markers for tracking the evolution of marine environments. They thus allow researchers to better understand the ecological changes of the period. The clay formation of Fezuata in eastern Morocco harbors an exceptional fauna similar to that of the Burgess Shale. The subtropical climate favored marine life in shallow coastal areas. Among the fossils, the arthropod Egirocassus, which reached up to 2 meters, stands out with its segmented body and filtering appendages. This discovery testifies to the rapid diversification of animal morphologies at the dawn of the Tremadocian, offering a fascinating glimpse into early complex life forms in prehistoric marine environments. Egirocassus represents a striking example of a plankton-eating organism filtering particles in warm waters of about 20 hectoliters, typical of early Ordovician. The local fauna also includes aberrant echinoderms that differ from modern forms like starfish and sea urchins. These creatures possess unusually arranged skeletal plates, illustrating evolutionary pathways still in development at this time, reflecting the biological diversity of the Carboniferous. At Fezuata, clay sediments deposited in calm basins favored the rare preservation of soft tissues due to rapid burial and a regular supply of sediments. This allowed for the preservation of high marine biodiversity despite environmental fluctuations. In 2022, a new geological section at Taichout, a nearby site, revealed a 10-meter stratum. Researchers are studying the continuity of the deposits there, thus offering an extended perspective on the evolution of these marine communities over a much longer period than previously thought. The recent discovery at Taichout allows better understanding of how Tremadocian organisms adapted to fluctuations in sea levels and chemical variations in the waters. The data show a succession of clayey and sandy layers, indicating climatic and sedimentation changes. The epicontinental seas that covered vast parts of the continents shifted repeatedly. In this context, the fauna, marked by Cambrian diversification, had to constantly adapt. The fossils of Fezuata provide a unique perspective on this fragile and dynamic equilibrium. The The Tremadocian is marked by tectonic processes, influencing the evolution of ecosystems. The supercontinent Gondwana begins to fragment, causing subductions along the magmatic system of Terra Australis. This phenomenon, where an oceanic plate slides under a continental or oceanic plate, generates volcanic activity and mountain uplift. These movements continue to shape the planet, altering the distribution of seas, continents, and the migration routes of marine fauna, profoundly impacting ecosystems. Epicontinental seas, associated with sustained tectonic activity, created marine corridors that facilitated the dispersion of species. For example, primitive graptolites thrived thanks to the circulation of nutrient-rich waters. Phosphatized microshells show adaptation to specific chemical conditions linked to the transport of phosphorus from emerging continents. These marine connections allowed organisms to explore new territories, stimulating biodiversity and laying the groundwork for the biological innovations of the Ordovician, thus marking the acceleration of marine species diversification. The Fezuata site serves as a laboratory to analyze ecological interactions in the Tremadocian. The clays preserve fossils detailing mineralized structures, traces of cuticles, and soft tissues, allowing the reconstruction of animal lifestyles. For example, the filtering appendages of the arthropod Aegirocassis suggest a diet based on suspended particles in the water, a strategy comparable to that of modern manta rays. This illustrates similar functional solutions developing across the ages of terrestrial life. The extraction of the Aegirocassis fossil is compared to that of an antique car mold trapped in the mud. At 2 meters long, this arthropod far exceeds the size of current arthropods. Paleontologists use chisels and hammers to remove the rocky matrix, a meticulous and lengthy task. When the contours of the animal emerge, its uniqueness is revealed, a massive creature, but subtly adapted to its marine environment. This discovery highlights not only its size, but also the adaptability of early Tremadocian fauna. The Tremadocian, although less known than other geological periods, is crucial in the evolution of our planet. It is a time when Cambrian groups diversify their forms, while new lineages emerge. Dendroid graptolites are essential bioindicators, indicating water quality and current circulation. These fossils play a fundamental role in the study of marine ecosystems, offering us a valuable understanding of the structuring of these communities, secrets still buried in the oceanic depths for millions of years. The Tremadocian represents a pivotal period where the evolution initiated in the Cambrian is affirmed. Faunas with phosphatized microshells, dendroid graptolites, and creatures like Aegirocassis testify to the diversification of the Ordovician. Under the influence of shallow seas and tectonic processes, marine life becomes more complex. The sediments of Fezuata, offering exceptional fossilization, allow the reconstruction of these buried worlds, prefiguring a key paleo-environmental scenario for the Ordovician. The Floian, spanning from 477.7 to 470 million years ago, constitutes an essential phase of the Ordovician. It is during this stage that the Great Ordovician biodiversification event unfolds. This is a major turning point where many marine organisms diversify to occupy varied ecological niches. At that time, Earth experienced a very warm climate, without ice, related to a high level of atmospheric carbon dioxide. The Ordovician thus becomes a true laboratory of biological innovations. The Floian, the second stage after the Tremadocian, is crucial for understanding future changes in marine ecosystems. To understand the importance of the Floian, one must first imagine the Earth as it was around 477 million years ago. Continents, in constant motion, did not resemble those of today. In the southern hemisphere, vast landmasses came together to form the supercontinent Gondwana, while others, like Laurentia or Baltica, drifted at different latitudes. Oceans largely dominated the globe, and numerous shallow epicontinental seas covered parts of the emerging lands. Under a warm climate, these waters housed flourishing ecosystems where various groups of animals and algae diversified rapidly. At the heart of this dynamic, one of the most fascinating fossil records of the Floian is located in the Montagne Noire, in the south of France. There, in layers dating back approximately 470 million years, is a site called Cabrieres Biota. Biota refers to the collection of living organisms at a given time, while the German term Lagerstätte refers to a remarkable fossil deposit, often preserving soft parts usually lost. In 2024, new research confirmed that Cabrieres Biota is indeed a window into the distant past, described as a polar assembly with ferric preservation of soft organisms, a term rich with meaning for paleontologists. To fully grasp this title, it's necessary to analyze each element. First, the mention of polar suggests that the site was at a high latitude during the Floian, close to colder environments than other deposits of the same era. According to paleogeographic reconstructions, the future Montagne Noire was then part of a continental sector located far to the south of Gondwana, in an area that probably experienced temperate, even cool climates at times. Next, ferric preservation refers to the manner in which the fossils were conserved. Generally, only hard elements, shells, carapaces, endure through time, whereas soft tissues decompose rapidly or leave faint traces. At Cabrieres, iron-based minerals covered some organisms, forming a protective mold around fragile parts, such as appendages or internal organs, allowing for a detailed study of the anatomy of beings that disappeared hundreds of millions of years ago. Among the more than 400 specimens discovered at Cabrieres, there are sponges, simple aquatic animals without specialized organs. They attest to the richness in nutrients and dissolved oxygen of the ecosystem. These sponges, powerful biological filters, capture suspended particles and reveal that there was enough organic matter and minerals in the water to sustain a complex food chain. Next are the Lobopodians, worm-like animals with segmented, flexible legs, today represented by forms like tardigrades or onychophorans. These creatures are crucial to understanding the early stages of diversification of segmented body animals. Paleontologists have also discovered non-mineralized trilobites, a rarity since the majority of these animals possessed a mineralized exoskeleton. This peculiarity shows how exceptional the sedimentation and preservation conditions at Cabrieres were, allowing even the most fragile forms to be captured. These discoveries are crucial to better understanding the cold ecosystems at the beginning of the Great Ordovician biodiversification. Although the Ordovician was generally warm, some regions experienced cooler waters. Several geological clues indicate that the Cabrieres communities evolved in a temperate environment, less subjected to the intense greenhouse effect observed elsewhere. Geochemical analysis of rocks and fossils leads scientists to consider this assembly as a rare example of marine diversity in less warm conditions, thus enriching our understanding of the varied marine environments explored by Ordovician organisms. Parallel to these fossil ecosystems in France, the Floian sees the appearance and expansion of armored fish, known as arandispids. Discovered in central Australia, Arundaspis illustrates this primitive stage with a bony shield protecting the head and trunk. It is not a complete skeleton, like in more evolved bony fish, but a precursor, showing nature's first attempts to reinforce vertebrate bodies against predation. Before them, marine life was dominated by invertebrates, often protected by shells or mineral carapaces. The Arundaspids mark a decisive step towards the emergence of vertebrates, which would later occupy a major place in evolution, both in water and on land. In 2024, studies reveal other microvertebrates in the Amadeus Basin, Central Australia. Tiny fossil scales and teeth, often only a few millimeters, provide valuable clues about the diversity of primitive fish associated with Arundaspis. Their extraction requires fine sieving and the use of weak acids to dissolve the rock without damaging these fragile remains. Observed under the microscope, the precise shape of the scales and teeth allows for the identification of different genera of armored fish. This diversity, which appeared early in the Ordovician, enriches the understanding of vertebrate diversification, which would intensify over millions of years to come. Besides primitive vertebrates, marine life experiences notable effervescence among reef builders. In the Cambrian, archaeocyaths, filtering animals resembling small perforated corals, dominated primitive reefs before disappearing at the end of this period. In the Floian, new communities take over, formed by stromatoporoids and cyanobacteria. Stromatoporoids, massive calcareous sponges, secrete a skeleton of superimposed layers, while cyanobacteria, simple photosynthetic bacteria, form stratified structures called stromatolites, contributing to the consolidation of the marine substrate. Their role is often underestimated. However, they have been shaping the chemical balance of oceans for billions of years by releasing oxygen and trapping carbon dioxide. The encounter between stromatoporoids and cyanobacterial mats results in true mixed reefs, creating habitats for a range of sedentary and vagal organisms. In the interstices of these constructions, mollusks, brachiopods, and arthropods find refuge and food. On the scale of the Floian, this diversification of reef builders is not yet as impactful as it will be later in the Ordovician. But it constitutes a crucial milestone towards the complexity of marine communities. Some of these coral or sponge structures will greatly develop in the following stages, showcasing the rise of reefs in the Middle and Upper Ordovician. Life thrives in the seas of the Floian, thanks to a climate termed as supergreenhouse. This term, supergreenhouse in English, describes a situation where the concentration of carbon dioxide in the atmosphere exceeds that observed even during less intense warming phases. Estimates suggest that, during the Floian, carbon dioxide was more than 10 times more concentrated than during the pre-industrial era, before human activities impacted the atmosphere. In practice, this led to very high average global temperatures, perhaps several degrees higher than today, and a world free of ice caps, both at the North and South Poles. In this planet covered with warm oceans, ocean circulation is more vigorous, and marine ecosystems develop in all directions. The tepid waters allow some creatures to colonize vast spaces, while other organisms benefit from strong primary productivity induced by the abundance of sunlight. Algae and cyanobacteria, through photosynthesis, produce significant quantities of oxygen, thus supporting the growing complexity of marine fauna. One can imagine shallow seas with substrates covered in nutrient-rich sediments, housing a variety of animals, from small burrowing invertebrates to hunting arthropods in search of organic debris. Fossils, particularly those preserved in sites like Cambrian, allow us to reconstruct these ecosystems and reveal their great diversity. This profusion of life and habitats, supported by a warm climate and a high concentration of carbon dioxide, fits perfectly into the Ordovician biodiversity boom. When discussing the start of the Go-BE, paleontologists emphasize how the Floian sparks the major evolutionary changes that will continue throughout the Middle Ordovician. We see the development of more diversified ecosystems, more complex food chains, and increased competition for space and resources. Armored fish illustrate the adaptive response to this competition, while stromatoporoid and cyanobacteria reefs demonstrate the ability of simple organisms to build refuges for other faunal communities. It is important to remember that this period does not resemble our current world from a terrestrial perspective. The emerging lands are still sparsely vegetated, with mainly microorganisms and some traces of primitive pioneering vegetation in wet areas. Life develops mainly beneath the waves, where marine currents disperse larvae and spores over long distances. The ocean remains the main stage for the rapid evolution of species. In the depths, the water chemistry fluctuates depending on the input of organic matter and stratification phenomena. Moreover, recurring currents and moderate variations in sea level sometimes create environments conducive to fossilization. As in Cambrian, chance has trapped and preserved countless creatures, including their soft tissues. Without these particular sedimentation conditions, we probably wouldn't know anything about the Lobopodians or non-mineralized trilobites of the Floian. The emergence of new predators with shells or bony plates puts pressure on animals lacking means of defense. We gradually observe the appearance of flight, camouflage, and mutual assistance behaviors among species seeking to protect each other. Sponges, for example, host auxiliary fauna on their surface or in their cavities, which benefit from their calcareous structure to hide. Brachiopods, these invertebrates anchored by a pedicle, develop more hermetic closing mechanisms for their shells. Trilobites, on the other hand, evolve by strengthening their dorsal segments or by burrowing further into the substrate for safety. This constant struggle partly explains the emergence of many specialized lineages, which, in a few million years, give rise to unprecedented biodiversity in Earth's history. As we advance through the Floian, changes in water chemistry manifest. Sediments record compositional variations, reflecting fluctuations in nutrient inputs and suspended matter. For example, limestones are deposited according to phases more or less rich in planktonic organisms. Terrigenous layers, laden with materials from the erosion of continents, alternate with carbonate layers, illustrating possible small-scale climatic changes or local tectonic movements. Thus, the history of the Floian is not linear, but unfolds through sequences punctuated by short-term disturbances, sometimes regional, sometimes global, affecting marine environments. Despite these fluctuations, the super-greenhouse effect remains the dominant factor, keeping the planet in a warm phase, devoid of ice caps. This absence of polar ice facilitates the dispersion of species, as ocean basins communicate more easily. The drift of continents also creates marine corridors, allowing exchanges between distant territories. However, endemic faunas exist, particularly in polar regions or partially isolated basins, like the polar assembly of Cabrières in France. Fossils discovered at these sites highlight the importance of studying varied geographical regions to grasp the globality of the diversification process. Without collecting data from different continents at the same time, we could not fully understand the diversity of the Floian, nor the geographical and ecological distribution of these ancient life forms. The Floian illustrates spectacularly how marine life adapts to a changing world. The exceptional preservation of fossils, as seen in Cambrian, provides paleontologists with tangible evidence of the richness of these ecosystems. very different organisms such as sponges, lobopodians, and non-mineralized trilobites coexist and thrive in an environment sometimes described as polar. This demonstrates the biological flexibility of Ordovician animals, capable of conquering a wide range of temperatures and environments. The appearance of the Arundaspidans, with Arundaspis as their emblematic figure, marks the beginning of an evolutionary adventure that will eventually lead to the extraordinary diversity of fish, then the first tetrapods, and finally, to terrestrial life as we know it. If an essential conclusion were to be drawn, it would be that the Floian marks the beginning of an explosion of marine forms in the oceans. It is supported by an extremely hot climate, akin to a tropical greenhouse where ice caps have no place. Reefs thrive in warm waters, rich in carbon dioxide, fostering the formation of impressive limestone structures supported by stromatoporoids and cyanobacteria. At the same time, the appearance of primitive vertebrates like Arundaspis confirms that competition for resources becomes a major driver of evolution, prompting life to innovate. Marine species must either strengthen their armors, refine their flight or defense strategies, or explore new environments less subjected to predatory pressure. Cambrian. Biota remains a privileged witness, proving that diversification is not limited to tropical marine zones. Polar ecosystems can also develop an unsuspected reservoir of diversity. Research conducted since 2024 shows that despite high concentrations of carbon dioxide, these environments manage to thrive. The expression ferric preservation of soft organisms highlights the unique fossilization mechanisms, allowing for the capture of fragile anatomical details. These details push the boundaries of our understanding of early animal evolution, offering access to forms and structures that wouldn't be found in poorly preserved specimens. The Dapingian, covering the period from about 470 to 467.3 million years ago, marks an intense phase of geological and biological activity within the Ordovician. This period is distinguished by a major meteoritic event, notable diversification of certain trilobite families, as well as the beginning of the tectonic orogeny, an episode of mountain formation. We will explain how these phenomena interact to transform the Earth in clear and accessible terms for an audience curious about this distant past. The first striking phenomenon of the Dapingian is the massive meteorite shower, known as the Ordovician meteorite event, occurring around 467 million years ago. These L-type chondrites, fragments from an asteroid in the main belt, contain silicates and iron oxides. Their sudden fall tripled the usual cosmic flux. The Österplana 65 meteorite, discovered in Sweden, is a famous testimony to this event. This flow of debris likely influenced the chemistry of the seas by introducing mineral particles capable of disrupting certain marine ecosystems. To confirm this finding, geologists study impact zircons, microscopic crystals, formed during the rapid melting caused by a meteorite impact. By dating them through uranium and lead isotopes, they determined the precise age of these violent events. On Slate Islands in Ontario, drillings have revealed zircons linked to this event, strengthening the hypothesis of a global ejectowave. This discovery indicates that Earth experienced an intense but short-lived extraterrestrial bombardment. Several researchers suggest that this massive influx of cosmic materials may have altered marine productivity and influenced the development of certain biological groups. As the sky unleashes its projectiles, trilobites experience a remarkable boom. During the Dapingian, the Asaphidae and Elenidae families thrive in the shallow zones of the Laurentia continent, located today in North America and Greenland. These arthropods, recognizable by their segmented exoskeleton, adapt to these environments and to food competition. Some filter sediments, while others move about to graze on small organisms. Their compound eyes, ability to curl up, and rigid exoskeleton make them perfectly equipped creatures for survival. This diversification demonstrates the excellent adaptability of trilobites in the face of a changing environment. Paleontologists decipher these expansions by studying fossil-rich deposits of trilobites. The Asaphadae have a broad cephalic shield and a thorax with mobile segments, sometimes allowing them to curl up for protection. The Elenidae, on the other hand, feature smoother shells. In marine deposits dating from the Dapingian, fossil clusters often align with ancient currents, indicating that trilobites formed dense populations exploiting nutrient resources. Their massive presence makes the Dapingian a significant stage in their evolution, heralding the effervescence of Ordovician biodiversity. Simultaneously, a major tectonic upheaval begins, the tectonic orogeny, the first mountain-building phase affecting the eastern margin of Laurentia, the future base of the Appalachians. During the Ordovician, the drifting and collision of plates lead to subduction, compression, and uplift. Rocks fracture, sediments move, and the crust deforms, gradually forming reliefs. This episode, beginning in the Dapingian, is part of the global dynamics of plate tectonics. As the crust rises, the exposed lands are subject to erosion. Rivers then transport significant quantities of sediments to the Iapetus Ocean, forming turbidites, suspended particle flows rich in nutrients. These marine deposits contain phosphorus, calcium, and other minerals, essential for the growth of aquatic organisms. Thus, although orogeny is a geological phenomenon, it indirectly nourishes marine life by releasing elements favorable to ecosystems, stimulating the growth and diversification of communities. In this context, trilobites, already prosperous, find ideal conditions to reinforce their presence in coastal areas. The Dapingian perfectly illustrates the interaction between physico-chemical changes, geodynamics, and biology. The sudden arrival of meteorites, evidenced by impact zircons at several sites, shows that Earth constantly interacts with its spatial environment. Simultaneously, the multiplication of certain trilobite families highlights life's adaptation to fluctuating marine environments. Finally, the emergence of a nascent mountain range, due to tectonic convergence, redefines topography and redistributes sediments. Each of these phenomena is remarkable, but their convergence makes this period particularly rich in lessons. Fossil records confirm that life continues to explore new modes of survival despite disruptions. From a documentary perspective, one can imagine these scenes as a grand film. While meteorites disintegrate in the atmosphere, trilobites with shimmering shields crawl over coastal plateaus, and tectonic crashes shake the underground. Eroded particles from the future tectonic ranges blanket the seabed, enriching the water with nutrients. We visualize an Earth in perpetual motion. Everything shifts, everything adjusts. This foundation is essential for history, as the transformations of the Dapingian pave the way for future biodiversity and the gradual metamorphosis of continental reliefs. Some scientists suggest that the bombardment of L-type chondrites brought metals and elements altering the local chemistry of marine basins at a crucial moment. They also estimate that these atmospheric impacts may have caused slight climatic fluctuations, indirectly influencing coastal biotopes. Whatever the case, this geological and biological conjunction illustrates the diversity of forces shaping life. From high subterranean pressures to stellar projectiles, The Dapingian is characterized by the coexistence of internal and external phenomena whose alliance creates an environment conducive to evolutionary innovations. When studying tectonic turbidites, grains transported over long distances are observed, testifying to the power of underwater density currents. These flows, loaded with sand and gravel, sometimes move at high speed, depositing a thick layer of sediments on the seabed. Trilobites capable of withstanding these conditions or quickly resettling after the flow's passage benefit from this. With each tectonic impulse, successive waves of deposits add materials, expanding the diversity of microhabitats. Thus, tectonics and evolution act in concert, nourishing the richness of Ordovician biodiversity. Ultimately, the Dapingian stands out as a major turning point in the Ordovician, marked by meteoritic impacts, the rise of marine arthropods, and the beginning of mountain formation. Trilobites from the Asaphadae and Elanidae families demonstrate life's adaptability to changing conditions. Type L chondrites recall the cosmic scale of these events. The tectonic orogeny initiates a long history of crystalline uplifts, leading to the Appalachian reliefs. Through the study of rocks, fossils, and minerals, we explore this distant episode in all its dimensions. This synthesis shows that Earth, even in its ancient times, is not a static sphere. It interacts with space, fragments under tectonic effects, and promotes biological diversity. The Dapingian reveals remarkable effervescence, both stimulated by a cosmic deluge and by ancient forces raising mountains. This period demonstrates how the randomness of celestial impacts and the regular drift of plates reshape ecosystems. For researchers, continuing the exploration of fossil deposits and impact traces is essential to understand how life thrived amidst these upheavals. Thus ends this insight into the Dapingian and its events. The massive passage of type L chondrites, the remarkable diversification of trilobites, and the beginning of the tectonic orogeny, three phenomena linked by complex balances that Earth constantly renews. This chronology unveils a world where the mechanics of planetary forces are already at work. It is a window into nature's incessant creativity. Each sequence reveals a new chapter of its history in motion. The Dapingian also signals the continuation of the great Ordovician biodiversification event, where interactions between species become more complex, foreshadowing richer and more robust ecosystems. The Darriwilian, from 467.3 to 458.4 million years ago, is situated at the heart of the Middle Ordovician. At this time, Earth's continental profiles differ from those of today, with land masses arranged differently and oceans covering vast areas. The biological proliferations of this period, often described as peaks of the Great Ordovician Biodiversification Event, GOBI, testify to a dramatic expansion of numerous life forms, especially in marine environments. To grasp the scale of this phenomenon, imagine a world where marine life occupies almost all ecological niches. Since the end of the Cambrian and the beginning of the Ordovician, many organisms have explored new ways of life, but it is especially during the Darriwilian that their groupings reach unprecedented complexity. Reefs develop, marine substrates diversify, and food chains become more complex. The rise of several groups, from Brachiopods to bryozoans to crinoids, is observed, forming an ever more varied fauna. Originally, the term brachiopod refers to a group of marine animals possessing two shells, often confused with those of bivalves. Unlike clams or mussels, their valve pieces are positioned dorsally and ventrally, rather than left and right. Under these shells, hide sophisticated internal apparatuses dedicated to filtering water and extracting nutrient particles. During the Darriwilian, many species of articulated brachiopods, so named because their valves are connected by a hinge, appear and develop. They thrive in shallow, nutrient-rich waters, benefiting from relative climatic stability and the expansion of continental shelves. Several lineages colonize varied sea bottoms, sometimes forming dense clusters that contribute to the creation of habitats where other creatures find refuge. Bryozoans, often called moss animals, illustrate this diversification well. These small aquatic beings live in colonies and secrete delicate, calcareous or organic structures. Each individual, or zooid, occupies a tiny chamber and uses its ciliated tentacles to filter water and capture plankton. In the Darriwilian, there is an explosion of these colonies across several regions of the globe, carpeting the seafloor and attaching to various substrates, rocks, abandoned shells, and other hard surfaces. Capable of forming extensive mats, bryozoans play a key role in structuring marine ecosystems, creating new ecological niches for many organisms. Scientists suggest that this spectacular rise could reflect an increase in nutrients linked to continental inputs or reorganizations of ocean circulation during the Middle Ordovician. Crinoids play an essential role in Darriwilian filter-feeding communities. Often called sea lilies, these echinoderms have a central calyx extending into long stalks that anchor to the seafloor and feature several branched arms to capture suspended food particles. Related to starfish and sea urchins, their skeleton is made of articulated calcareous plates. Although known since the early Ordovician, their diversification significantly accelerates in the Darriwilian, thanks to abundant nutrients and the expansion of reefs. Benthic complexity, meaning the diversity of the seafloor, offers them numerous opportunities for attachment. Thus, crinoids become major players in filter-feeding communities, thriving in many regions, benefiting from warm waters and a climate favorable to marine blooming. To describe the extent of this diversification, some specialists speak of a 3-digit growth in the number of genera, meaning that between the beginning and the end of the Darriwilian, this total more than doubled or even tripled according to estimates. This unprecedented biological boom sees each form of life occupying a particular niche. Predation relationships become hierarchical, food chains lengthen and become more complex, while symbiotic interactions gain importance. The result is a mosaic of interconnected biotopes, where the race for anatomical and adaptive innovation progresses at a brisk pace. At the heart of this period of excitement, the Winneshiek deposit in the state of Iowa, USA, reveals valuable clues about the creatures thriving at that time. This fossil site, described as a Lagerstätte, testifies to remarkable preservation, notably of soft tissues rarely preserved. Lagerstätte is a German term designating an exceptional deposit capturing a rich snapshot of an ancient ecosystem. The history of Winneshiek begins more than 460 million years ago when an underwater meteorite impact creates a crater. The collision hurls rock fragments, forming a ring breccia, a chaotic conglomerate of debris around the impact site. Gradually, water, likely low in oxygen, favors a particular preservation. Dead animals were quickly covered, allowing the conservation of fragile parts, such as soft tissues. Among the significant discoveries at Winneshiek is the first mention of certain eurypterids, nicknamed sea scorpions. These marine predatory arthropods possess paired flippers, sometimes a sting or spines. Their size ranges from a few centimeters for the smallest to over a meter for some large representatives appearing later in the Paleozoic. In the Darriwilian, these early eurypterids mark the rise of arthropods in coastal and shallow marine ecosystems. They likely occupied roles as active predators, hunting small and medium-sized organisms and contributing to the structuring of trophic networks. These fossils offer a unique glimpse of marine life of the time, revealing a great variety of creatures, from filter-feeding invertebrates to mobile predators equipped with pincers or swimming limbs. Meanwhile, other fossils preserved in this breccia testify to soft-bodied organisms, suggesting that the diversity of this environment far exceeded what the study of hard skeletons alone would have revealed. The Winneschik Lagerstätte thus sheds light on the extent of Darriwilian biodiversity, significantly enriching scientists' understanding of Middle Ordovician ecosystems. Without these traces of soft tissues, many chapters of marine evolution would have remained unknown. A notable paleontological treasure from the Darriwilian is the primitive fish Eryptychius, studied using advanced 3D tomography conducted between 2023 and 2024. This vertebrate is considered a stem gnatostom, an organism located at the base of the evolutionary lineage leading to jawed vertebrates. The term stem gnatostom refers to an intermediate link between jawless vertebrates and the earliest true jawed vertebrates, not yet possessing all the complete characteristics. Eryptychius thus represents a key stage in the evolution of jawed vertebrates. Thanks to 3D tomography, which reconstructs the interior of a fossil by overlaying multiple imaging slices, paleontologists observed, for the first time, the oldest known articulated neurocranium, dated to about 458 million years old. The neurocranium, the part of the skull surrounding and protecting the brain, is crucial for understanding the development of the nervous system and sensory organs in primitive vertebrates. The exceptional preservation of Eryptychius's neurocranium offers a rare opportunity to study the intracranial anatomy of an organism preceding the first true jawed fish. Researchers are reconstructing the shape and arrangement of brain cavities, intracranial blood circulation, and the organization of the inner ear. They thus provide valuable insights into the evolution of essential structures found in modern vertebrates. This discovery reinforces the idea that the Darriwilian is not only a period of flourishing marine invertebrates, but also a pivotal moment for innovation among primitive vertebrates. The data show that jawless fish coexist with the first representatives of jawed lineages, outlining a diversification that will continue throughout the Paleozoic. Eryptychius embodies this period of transition and illustrates the wonder inspired by modern imaging technologies, capable of revealing both literally and figuratively the minutest details of ancient biology. Despite this golden age of biodiversity, geochemical analyses show that the equilibrium was not stable during the Darriwilian. Recent studies, conducted in 2025 on the Yangtze platform in China, have revealed a negative carbon isotopy of 2% zero. This measurement reflects a decrease in the ratio between carbon-13 and carbon-12 isotopes, a possible indication of disturbances such as a massive release of light carbon, a rapid change in primary productivity, or a modification in ocean oxygenation. Researchers interpret this value as a marker of global carbon stress. In summary, during the late Darriwilian, marine ecosystems and oceanic chemistry experienced significant environmental fluctuations, visible in the isotopic composition of the rocks from that time. Carbon stress refers to an imbalance in the carbon cycle affecting photosynthesis, respiration, or the formation and dissolution of carbonates. When an excess of light carbon, carbon-12, dominates, it can result from massive degradation of organic matter, volcanic episodes, or other phenomena releasing large amounts of carbon dioxide into the atmosphere and oceans. This excursion reflects an increased sensitivity of the biotopes. Some species resist, while others suffer the effects of upheaval. In surface waters, a sudden nutrient influx or temporary anoxia may alter the distribution of fauna and flora. Filter-feeding invertebrates, like brachiopods and crinoids, adapt better if benthic conditions remain stable, whereas other more specialized populations may suffer. Additionally, the concentration of carbon dioxide influences water chemistry, impacting the formation of calcareous skeletons and the physiology of sensitive organisms. These alterations to the carbon cycle, though not catastrophic in the short term, reveal the fragility of the Ordovician biosphere. Yet, despite this carbon stress, global diversification continues during the Darriwilian. Fossils bear witness to significant biological richness with an increase in families, genera, and species. Reefs form, food chains enrich, and new evolutionary innovations appear. This paradox, combining marine prosperity and chemical perturbations, illustrates that evolution often progresses in an unstable balance, where environmental changes and adaptive leaps coexist. The delicate balance grants the Darriwilian its status as the pinnacle of the great Ordovician biodiversification event, a peak from which other evolutionary transformations emerged. The numerous lineages of filter-feeding invertebrates or jawed fish precursors owe their success to a combination of biological and geological factors. Continents drift, shaping new epicontinental seas. Ocean currents transport sediments, nutrients, and temperature variations into scarcely exploited marine habitats. The cycles of marine transgressions and regressions modulate depth, salinity, and environmental stability. Animals adapt, specialize, and disperse, developing new strategies for feeding, reproduction, movement, or defense. Recent discoveries emphasize the crucial role of paleontological and geochemical research. They demonstrate how the study of exceptional deposits and the use of advanced imaging technologies renew our understanding of a period several 100 million years old. In the Darriwilian, everything converges. The abundance of marine invertebrates, the consolidation of bryozoan colonies, the flourishing of articulated brachiopods, the radiation of crinoids, and the progressive emergence of vertebrates with innovative traits. All of this takes place against a backdrop of isotopic upheavals that shape the geological record. For us 21st century observers, this chapter in the history of life fascinates with how nature, even in an ancient world order, managed to experiment with innovations and weave complex networks of interactions. In detailing this great taxonomic burgeoning, we realize that many of the current traits of animals have roots far back in time. The anatomical features forming stalks, arms, jaws, or internal structures partially emerged in these ancient creatures. The geological archives of the Darriwilian testify to the ability of our distant ancestors to conquer various evolutionary domains, despite an environment often marked by chemical and climatic mutations. The Darriwilian appears as a key stage in understanding the diversification of life on Earth. Evolutionary pressure results not only from competition between species, but also from external factors, such as variations in the carbon cycle. While invertebrates proliferate in emerging reefs and seafloors, some vertebrate lineages lay the foundations for major innovations. Eurypterids, predators, foreshadowing future giant marine arthropods, embody this evolutionary dynamic that shapes ecosystems. Simultaneously, within the sediments, Euryptychius provides a crucial anatomy lesson on the appearance of advanced cranial structures in future jawed fish. Tracing the chronology of these discoveries captures the distinct atmosphere of the period. First, brachiopods, bryozoans, and crinoids proliferate. Then, the Winneschik Lagerstätte reveals exceptional fossils, shedding light on the journey of eurypterids and other soft-bodied animals. Finally, in-depth studies highlight a carbon stress, detected through isotopic analysis, suggesting significant environmental fluctuations. In a mere few million years, the planet thus forges entire segments of the biosphere that will deeply influence the remainder of the Paleozoic. In conclusion, the Darriwilian stands out as an exceptional moment when marine life, propelled by the great Ordovician biodiversification event, explores remarkable adaptations. Recent research confirms the importance of this period for understanding the distant past. Whether it's articulated brachiopods, bryozoans, crinoids, or eurypterids, each discovery enriches the puzzle of evolution. Paleontologists, geochemists, and other specialists of ancient Earth have a flourishing field of study where the richness of fossils intertwines with the geochemical variations of rocks. By bringing together these clues, we uncover a world where, despite isotopic and climatic upheavals, life continues to diversify and fully occupy the marine horizon. In this story, Euryptychius embodies the hope of uncovering the secret of the early stages in the formation of an articulated skull. His fossilized neurocranium, reconstructed using 3D tomography, illustrates the potential of digital paleontology to revisit fundamental notions of anatomical evolution. This fossil is not a fixed object, but a witness waiting for the right technology to reveal its message. It demonstrates how small clues, scattered in sediments several 100 million years old, can upend classic models and shed light on some mysteries of vertebrate phylogeny. To visually imagine the Darriwilian, envision a vast ocean where colonies of bryozoans cover the seabed with a living carpet undulating with the currents. Above, graceful crinoids extend their arms to collect plankton and food particles, while banks of brachiopods fixed on hard surfaces open their valves to feed. Among these filter feeders, more mobile creatures, such as opportunistic eurypterids, seize an unwary prey gliding through the water. In the deeper layers, far from sight, a strangely shaped fish, Euryptychius, whose primitive neurocranium is set to travel through millions of years to reach us, is a precious fossil rediscovered by modern science. It is in this context that one of the most fertile pages in marine life's history is written. The Darriwilian, the peak of the great Ordovician biodiversification, gathers the key factors of a biodiversity explosion: varied marine environments, a relatively stable climate despite some disturbances, vast habitats on continental shelves, and major biological innovations gradually outlining the complexity of future life forms. At the same time, significant changes in the carbon cycle, signaled by the famous 2% zero signature, remind us that the planet is subject to constant transformations, forcing the Darriwilian fauna to adapt to these fluctuations. Such is the backdrop of the Ordovician world, whose memory is inscribed in rocks, fossils, and isotopic compositions. By unveiling this age, we better perceive the dynamics of a distant universe, closely linked to our understanding of current biodiversity. The Darriwilian constitutes a natural laboratory where key groups emerge and rapid evolution phenomena are deciphered in an ever-changing environmental context. The legacy of this period resonates in our research, illustrating how life flourishes despite the challenges imposed by Earth and space. If invertebrates blossomed into diverse forms and vertebrates began their ascent, it is because, even in adversity, evolution constantly invents new solutions. The Darriwilian remains a pivotal moment that shaped the living world and continues to fuel our thirst for knowledge. The Sandbian, the geological interval between 458.4 and 453 million years ago, marks a phase where marine life reaches new heights of gigantism, with the emergence of imposing creatures in shallow seas. The continents, then arranged differently, experienced a maximum eustacy, that is, a global rise in sea level, forming vast interior seas and isolating continental cratons. In this world primarily covered by shallow waters, several marine groups experienced spectacular development, illustrating the vitality of Ordovician biodiversity. To better understand this paleo-environmental context, let us recall that eustacy, a global variation in sea level, depends partly on climate and tectonics. During the Sandbian, the absence of significant polar ice and the strong geological activity related to the reorganization of continents raised the coastline. Warm, shallow, and well-lit waters thus formed favorable habitats, rich in nutrients and space, allowing many animal lineages to expand and occupy various ecological niches. In these lagoons emerged major protagonists, including orthocone cephalopods, with Cambrian as a superpredator. These marine mollusks had an elongated, often straight shell, which could exceed 6 meters in length, a gigantic size for the time. In these shallow waters, this animal propelled itself using a siphon system expelling water, controlling pressure in chambered sections along the shell. This jet propulsion gave it power and agility, allowing it to stay above the seafloor and hunt like a modern giant squid. Unlike current squids, Cambrian retained this imposing mineral shell, providing support and buoyancy regulation. Its appearance was likely quite impressive to potential prey schools. Although its exact morphology remains partially hypothetical, most paleontologists believe it possessed a powerful beak, muscular tentacles, and strong suction capacity. This allowed it to catch and consume various organisms, from arthropods to primitive vertebrates. These superpredators of the Laurentian shelves dominated a vast territory, benefiting from the epicontinental seas that covered a large part of the continents. Thanks to their size and hunting abilities, they exerted significant selective pressure on populations, likely provoking defensive adaptations in their prey. In this complex balance, the predator-prey dynamic helped structure the marine communities of the Sandbian. Furthermore, Cambrian was not the only claimant to supremacy. Asteroids, or sea stars in a broad sense, also experienced significant development during this period, integrating into the ecological mosaic of the nascent reefs. Asteroids are echinoderms, a group also including sea urchins, sea cucumbers, and crinoids. Their body, organized around a 5-part radial symmetry, demonstrates great regenerative capability and remarkable adaptability. Researchers estimate that the Sandbian sea stars lived on or near the seafloor, sometimes clinging to reef fragments for better access to food, mainly composed of small organisms and organic debris. Their appearance likely coincided with the expansion of ecological niches and the rise of bioconstructed reefs, structures formed by the accumulation of skeletons or biological remains. Unlike modern coral platforms, the nascent reefs of the Ordovician were dominated by tabulate corals and various calcareous organisms whose distribution and morphology varied according to depth and light. Tabulate corals were distinguished by horizontal partitions delineating internal chambers. Though modest during the Sandbian, these corals would become a major group in reef formation throughout the Paleozoic. Their establishment marked a key stage towards increasingly complex reef ecosystems. As mixed reefs and other pioneering organisms formed, new habitats multiplied, favoring the evolution of more sophisticated life strategies. These reefs offered nooks, crevices, and solid substrates, providing shelters for young animals and supports for sessile species. This environmental diversity reinforced biomass and interdependence among marine lineages. Asteroids, with their varied diet and ability to ingest nearly everything under their arms, played an active role in the circulation of organic matter. They sometimes regulated the excessive proliferation of hermatypics and other sessile invertebrates. This network of interactions gradually shaped the foundations of reef life as we know it today. In this world inhabited by specialized beings, the gigantic arthropod Megalograptus dominated the Ordovician seas. These eurypterids, nicknamed sea scorpions, although not strictly scorpions, were distinguished by a segmented body, pincers, and sometimes a long, spiny tail. Megalograptus possessed an impressive chelate pincer, measured at about 45 centimeters. This powerful weapon allowed it to grasp and tear apart its prey. In shallow waters, it probably occupied a high trophic rank, hunting or scavenging. Like many arthropods, it was protected by a chitinous exoskeleton, sometimes reinforced by minerals, supporting its weight in the water, but imposing constraints during molts. This adaptability allowed it to thrive in various geological contexts, making Megalograptus a remarkable example of evolutionary success. The existence of these superpredators, orthocone cephalopods and eurypterids, reveals how the Sandbian period saw food webs expand and gain complexity. Filter-feeding organisms, small crustaceans, brachiopods, and other groups were part of this web of life, fostering the emergence of dynamic ecosystems. Thanks to a warm and stable climate, coupled with a high concentration of carbon dioxide in the atmosphere, marine primary productivity remained high. Algae and photosynthetic microorganisms played a key role in the food chain by their abundance, indirectly nourishing invertebrates and supporting the rise of larger animals for whom food was plentiful. This biological vitality left fossil traces in the sedimentary rocks formed during this time. The Laurentian platforms refer to continental masses originating from the supercontinent Laurentia, corresponding today to North America and some adjacent territories. During the Sandbian, Laurentia was located in a temperate to tropical climate zone, encouraging the development of vast marine systems rich in biodiversity. The clear waters allowed photosynthesis, feeding reef communities, while interconnected marine corridors facilitated species dispersion. Although formidable, the superpredators were not invincible. Fossils sometimes show marks of injuries, failed attacks, or competitions between individuals, highlighting the harshness of the marine environment despite the abundance of food. Geologically, the Sandbian is characterized by a high sea level that generated thick sedimentary formations, notably fossil-rich limestones. Various faunal assemblages provide clues about the depth and salinity of the waters. Moreover, fine sediments trapped remains of arthropods, mollusks, and primitive fish, offering valuable information on fauna evolution. This marine transgression, or sea encroachment onto land, thus left remarkable fossil archives that shed light on this ancient world. Here we are in the Katian, a period ranging from 453 to 445.2 million years ago. This pivotal time is marked by significant climate changes and the appearance of tiny yet essential plant forms on damp lands. The Katian reflects a gradual cooling, accompanied by a notable drop in atmospheric carbon dioxide. Simultaneously, immense reefs composed of tabular and stromatoporoid organisms arise, forming imposing carbonate platforms in various regions of the globe. To understand these phenomena, one must first grasp the geological context. The southern hemisphere continents, grouped under Gondwana, saw their polar zones covered by vast ice caps. This cooling, initiated before the Katian, intensified, leading to sea level drops in several regions. Powerful sedimentary remobilizations occurred, giving rise to Katian turbidites, observed notably in certain basins of present-day southern Europe. These marine deposits, rich in terrigenous sediments, testify to the significant volume of materials eroded from the continents. Amidst these upheavals, small microscopic structures called cryptospores emerge, the first direct evidence of non-vascular plants, comparable to present-day mosses. These spores indicate the probable presence of bryophytes, pioneers colonizing the damp edges of emerged lands. Their ecological role is crucial. They stabilize soils and partake in carbon dioxide trapping. Moreover, they provide essential support for the development of larger organisms that would appear in subsequent eras. During the Katian, a continuous decrease in carbon dioxide, linked to the expansion of the first land plants, profoundly altered the climate. These plants, especially bryophytes, trapped organic matter, slowing its decomposition and facilitating its burial in soils. At the same time, the chemical weathering of rocks, especially in humid areas, further reduced atmospheric CO2. This dual action caused a marked cooling, particularly in the southern hemisphere, where glaciers advanced. At this time, the construction of tabulate stromatoporoid reefs reached impressive proportions. These calcareous sponges, associated with primitive tabulate corals, built immense reef structures, sometimes over 100 kilometers long and high, forming true biological citadels. The fossils of these massifs, visible in Estonia and China, testify to a past where marine life adapted to environmental variations, offering refuge to many species and protecting large lagoons. These reefs illustrate the robustness and diversity of marine communities. Competition for space and light stimulated the evolution of fixed organisms, while new predators exploited the relief of the reef barriers. The circulation of nutrients was constantly reorganized according to changes in sea level, mainly related to the movements of polar ice on Gondwana. The thickening of ice sheets increased frozen water, reducing liquid water in the oceans and causing local marine regressions. Turbidites formed when significant sediments slid from continental slopes into the depths, often triggered by storms or earthquakes. These successive deposits revealed continental erosion and the vigor of cold climates. Moreover, the particles resulting from rock weathering trapped carbon dioxide, closely linking sediment dynamics to the climate. Thus, the climate system and sedimentation evolved in concert during this period. Despite global cooling, marine life continued to thrive in the warm waters of low latitudes. Tabulate stromatoporoid reefs, particularly resistant to variations in temperature and oxygen, housed a great diversity of species, from filter feeders to specialized predators. Fossils bear witness to this ecological richness and adaptations to environmental changes. In cold areas, some species strengthened their integument or adopted strategies to survive the resource decline linked to the retreat of sea levels. On the humid margins of continents, plant cryptospores marked a turning point in the colonization of emerging lands. Although confined to low and humid areas, these plants began to transform barren soils by forming organic layers that retained moisture, protected the soil, and created a microhabitat favorable to other organisms. Bryophytes, in association with certain fungi, improved nutrient absorption. This slow process, long-term, prepared the appearance of the first forests. The accumulation of ice on Gondwana profoundly affected oceanic circulation. While equatorial waters remained warm, the thermal contrast with the poles increased, strengthening winds and currents and modifying the distribution of oxygen and nutrients. This dynamic favored plankton productivity in illuminated areas, but reduced it in turbid waters. Moreover, the expansion of sea ice increased the albedo, reinforcing the global cooling of the planet. In regions like Ohio, Katian limestone deposits revealed treasures, including fossil amber chains from resins produced by extinct coastal microforests. Formed in hardened droplets, this amber accumulated in Ordovician coastal sediments and was rapidly buried, avoiding degradation. For paleontologists, these fragments are precious witnesses of plants secreting protective substances, indicating an already rich and complex terrestrial biodiversity. The anecdote of fossil amber reveals a major transition in the Katian. As cooling reduced inland seas and their reefs, coastal areas expanded, allowing new plant communities to establish. Cryptospores and fossil resins testify to the transition from a marine world to an environment where shores and humid soils hosted increasing diversity. These pioneers, although very different from future giant forests, already illustrate life's determination to colonize every corner of the Earth. Scientific research emphasizes that the Katian is a crucial period for understanding the balance between the atmosphere, oceans, and the nascent terrestrial biosphere. Isotopic analyses reveal a close link between the expansion of ice in the South Pole and the gradual decrease of carbon dioxide. Even small groups of primitive plants contributed to capturing this carbon, paving the way for future plant expansion. At the same time, massive reefs show the ongoing adaptation of marine fauna in the face of ecological changes. Around 445 million years ago, at the end of the Katian, the world enters a phase of global cooling. Polar ice caps extend, altering coastlines and deepening the thermal contrast between the equator and poles. Marine ecosystems regress, pushing some organisms to migrate. On land, the first plants continue to take root, preparing for future plant expansions. The Katian demonstrates the ability of life to adapt in the face of a changing climate. The Hirnantian, between 445.2 and 443.8 million years ago in the Ordovician, is marked by intense climate upheavals and mass extinctions, followed by ecological rebound. This period is characterized by the Pan-African glaciation, major biological crises, and astronomical mechanisms influential on life. The Earth then experiences rapid expansion of polar ice caps, a sharp drop in sea levels, a reorganization of marine habitats, and a double extinction crisis. The fossils of the Soom Shale in South Africa offer a rare glimpse into the marine fauna of this time. This text details these events and the resilience of life. Before examining the direct effects of glaciation, let us recall that during the Hirnantian, most of the southern hemisphere's lands formed the supercontinent Gondwana. The latter was drifting toward higher latitudes, favoring the gradual installation of ice. Polar caps extended down to 30 degrees south, bringing cold even into temperate zones. mountains and plains were covered with glaciers, a phenomenon reinforced by the drop in carbon dioxide, which reduced the greenhouse effect and stabilized this cooling. The glaciation results in a sea level drop of more than 70 meters, widely exposing continental shelves, an exceptional phenomenon. The shallow waters, once rich in corals, Brachiopods, and Trilobites, become cold desert zones, sometimes covered with seasonal ice flows. This retreat isolates aquatic populations, restricting exchanges between basins. This fragmentation decreases their resilience, playing a key role in cascading extinctions due to rapid ecological changes. Geological records reveal a key phenomenon, the Hirnantian isotopic carbon excursion, HACs, a sharp increase of carbon-13 isotope in marine sediments at the end of the Ordovician. This rise, exceeding 6%, is explained by a close link between glaciation and the carbon cycle. During cooling, more organic matter is sequestered in sediments, reducing light carbon in the ocean and atmosphere. Recent 2024 models associate this variation with the expansion of ice and the decrease of free oceanic surfaces. This shows how climate and biosphere are deeply linked. During the Ordovician, marine life, concentrated on continental shelves and shallow seas, faced a difficult context. Cooling, water retreat, and chemical fluctuations create a hostile environment. This causes a double extinction crisis, one of the most important ever known. The first episode, or pulse, corresponds to the peak of cooling, leading to the disappearance of many species unable to adapt, notably brachiopods, tabulate corals, and graptolites. The second extinction pulse is linked to the shock of anoxic backflow. Cooling changes ocean circulation, and after partial ice melting, massive land-derived nutrient inputs fall into the oceans. This causes anoxic episodes, making life difficult for many species. Non-decomposed organic matter accumulates in sediments, creating an imbalance. This second extinction affects groups that survived the first cooling. Together, these two waves form a major crisis comparable to major historical extinctions. Despite the severe extinctions of the Hirnantian, marine life persisted, as shown by the Soom Shale Formation in South Africa. This fine deposit from the end of the Ordovician offers remarkable preservation, called chemical mummification. It reveals cartilaginous chondrichthyans, ancestors of sharks and rays, and pycnogonids, small marine arthropods. Their near-perfect condition is the result of rapid deposition in oxygen-poor waters, which protected even soft tissues, allowing for rare and valuable paleontological discoveries. The particular chemistry of the deposits allowed for remarkable preservation, slowing the degradation of organic matter. Mineralizations of the soft parts, sometimes covered with phosphate films, preserve structures close to the living state, referred to as chemical mummification. These fossils show that Hirnantian biodiversity did not disappear. Certain species survived and evolved discreetly, heralding the Paleozoic. They offer paleontologists a better understanding of the resilience of ancient ecosystems, where life persisted even in the midst of a crisis. Recent studies indicate that astronomical cycles regulated climate fluctuations during the Hirnantian. An analysis published in 2023 reveals a correspondence between glaciation peaks and an orbital cycle of about 405,000 years. This cycle, influenced by the tilt and eccentricity of the Earth, controlled the advance and retreat of the polar ice caps, impacting sea levels and oceanic oxygen. During colder periods, the ice expanded, while warm phases caused melting and disrupted marine circulation. This shows that ecological crises also depend on celestial mechanics, not just terrestrial phenomena. During the Hirnantian, cooling, sea level drop, isotopic excursion, and double extinction crisis greatly fragmented the environments. Only species capable of withstanding cold, food scarcity, and anoxia survived. Among them, robust brachiopods, certain mollusks tolerant of chemical changes, and primitive fish with various survival strategies. The massive disappearance of species created ecological niches that the survivors would later exploit to diversify. As the last stage of the Ordovician, the Hirnantian is a pivotal period that disrupts marine life, ocean chemistry, and evolution. This phase of abrupt cooling and mass extinction serves as a scientific reference for studying biodiversity in the face of rapid climate changes. Despite planetary instability, life persists, finding refuges and exploring every viable space to survive and thrive. The Hirnantian thus illustrates the tenacity of life in the face of profound upheavals. The post-Hirnantian ecological rebound illustrates how life rebuilds after intense cold and oxygen scarcity. With the retreat of the ice, marine systems reconstitute and the temperature rises slightly, allowing for the establishment of continental shelf ecosystems. Biological productivity resumes, with new corals, brachiopods, and trilobites adapted to these conditions. The drop in sea level also favors the colonization of emerged areas. These changes redefine evolution and prepare the rich biodiversity of the Silurian with more resilient life. The Hirnantian shows that terrestrial evolution is not linear. Climate and biological crises cause major reorganizations in just a few 100,000 years. Astrochronology, by studying orbital cycles, helps understand the precise timing of these events. Through drillings, isotopic and fossil analyses, scientists reconstruct a past shaped by ice, marine chemistry, and astronomical influences. This period illustrates the Earth's ability to combine internal forces, like continental drift, and external factors, such as Earth's orbit, to create major upheavals. Over nearly 2 million years, this period is a natural laboratory for studying interactions between fauna, flora, climate, and geology. Imagine a journey through time, massive glaciers on multiple continents, rapid sea withdrawals, desolate plains, and the mass death of marine communities. Then, resilience appears. The ice recedes, life colonizes new habitats, and shows surprising adaptations. The survivors of this crisis play a key role in the following era. The Pan-African glaciation and a sea level drop of more than 70 meters caused profound climatic and ecological disturbances. The Heiss isotopic excursion reflects the interaction between ice, carbon, and ocean chemistry. The double extinction crisis drastically reduces marine biodiversity while paving the way for renewal. Rare fossils from the Soom Shale show the survival of atypical species thanks to exceptional preservation. Astrochronology highlights orbital cycles that regulate these upheavals. Beyond glaciers and marine deserts, the Hirnantian illustrates Earth's rapid ability to change. Faced with complex geological, climatic, and astronomical forces, living beings constantly reinvent themselves. This end of the Ordovician demonstrates how life endures major crises before renewing and exploring new paths. It is a striking example of collapse, followed by renewal, highlighting the fragility and tenacity of life. During the Ordovician, marine life experiences a spectacular explosion, with the number of genera tripling in 20 million years. Oceans teem with diverse organisms, occupying almost every ecological niche. This growth is not limited to numbers. It transforms interspecies relationships, complicating the food chain. Marine life transitions from a Cambrian invertebrate dominance to a rich network with various predators, herbivores, scavengers, and filter feeders. Biodiversity always depends on a balance between speciation and extinction. During the Great Ordovician biodiversification, the emergence of new species far outpaced the losses, causing a strong increase in diversity. This phenomenon is due to several factors: climatic changes, nutrient increase, and coevolution between predators and prey fostering innovation. Plate tectonics also created many shallow marine environments, conducive to the diversification and prosperity of organisms. During the Ordovician, marine life evolves with the emergence of better protected and more mobile animals. In the Paleozoic, Cambrian animals had thin shells, making them vulnerable, but the Ordovician marks a turning point. Several groups developed solid armor, such as the pterospidomorphs, primitive fish covered with plates called dermal bone. These armored fish, though small, were much more resilient than their ancestors, lacking such protection, changing marine dynamics. Pterospidomorphs are a key example of biological innovation. Their external carapace allowed them to occupy new marine habitats and escape predators. Their dermal bones, the first forms of external ossification in vertebrates, formed on the skin surface, distinct from modern internal bones. This protection promoted morphological diversification, with the emergence of sensory organs, articulated plates, and adaptations facilitating defense, feeding, and reproduction. Eurypterids transformed the Ordovician marine ecosystem. These segmented arthropods had appendages for swimming or walking on the bottom. Some had large swimming flippers and a tail called a telson. Related to modern spiders and scorpions, they played several roles: predators of invertebrates, scavengers probing the sediment, or prey for more evolved armored fish. Their diversity illustrates the increasing complexity of marine ecosystems at that time. The great innovations of the Ordovician also affect terrestrial colonization. Small pioneering plants, akin to modern bryophytes, appear discreetly out of freshwater. These microscopic cryptospores, capable of surviving in dormancy, bear witness to this venture. These robust plants, together with microbes, formed primitive soils that retained water and weathered rock. This process slowly paved the way for the subsequent expansion of more complex plants, marking the beginning of terrestrial life. It is impressive to see how small innovations in the Ordovician prepared the Earth we know today, rich in trees, flowers, and plants. These early plants, established on shores, altered the atmosphere by capturing carbon dioxide and releasing oxygen. By forming microbial vegetal soils, they laid the foundation for the later emergence of roots, robust stems, and dense forests. This terrestrial conquest begins with trilete spores found in coastal sediments. The gradual installation of the first plants indirectly influenced marine ecosystems by modifying erosion and the supply of coastal nutrients. The development of soils increased the transport of organic matter to the oceans, stimulating planktonic production and the food chain. This primitive vegetation also sequestered carbon dioxide, affecting the global climate. Despite its modesty, it played an essential role in the prosperity of marine life and in the future greening of emergent lands. In the heart of the Ordovician, diversification was not limited to plants and fish. Interactions between life forms became more complex, giving rise to new ecological phenomena. Among these, bioerosion stands out. Unlike physical or chemical erosion, it is caused by organisms that biologically bore into hard substrates like limestone, shells, or carapaces. These holes often serve as shelters, food sources, or protection. In Ordovician fossils, traces called Triponites and Osprionides borings are found. Borings are biological perforations made by marine animals, often worms or small organisms capable of drilling solid surfaces. Triponites refer to elongated fossil traces in limestone rocks or shells, while Osprionides correspond to channels dug by endolithic organisms, that is, living inside the stone or shell. The perforation of shells and skeletons marks a turning point. Organisms actively attack their prey to settle in. This evolutionary escalation sees prey reinforce their defenses with thick shells or chemical means, while borers improve their drilling capacity. The traces of Triponites and Osprionides borings testify to a complex and hierarchical food chain. This dynamic of constant innovation between predators and prey creates a dense and rich ecological network. Imagine an Ordovician brachiopod or mollusk on the seafloor, threatened by bioborers. Some species have reinforced their shells with thick walls and spines for defense. This ecological complexity has also favored innovations in the skeleton, nervous system, organization in protective colonies, and collective behaviors, as seen in bryozoans and trilobites. These adaptations continue to be studied today, notably thanks to 3D reconstruction from precise scanners of fossils. The Ordovician marks a major stage in the evolution of life, with organisms better protected, organized, and capable of conquering new environments. The pterospidomorphs embody armored fish, the eurypterids the diversification of arthropods, and cryptospores embody the emergence of the first wet soils, precursors to the greening of continents. Specialized bioerosion reveals complex interactions between species, even within shells. These evolutions, spread over millions of years, leave a profound trace still visible in the current fossil records. Some researchers consider that the remarkable diversification of the Ordovician, with its innovations in armor, locomotion, terrestrial colonization, and bioerosion, prepared the ecological dominance of the Middle Paleozoic. By promoting complex interactions, conquest of land, and diversification of invertebrates, this period paved the way for a new evolutionary stage confirmed in the Silurian and Devonian. Fragmentary fossils require reconstructions and comparisons with later species. Each discovery contributes to a better understanding of the diversity of adaptations. This faunal explosion was favored by the reconquest of marine niches, an active oceanic circulation, and a rich nutrient supply, linked to the geographical configuration of continents and epicontinental seas. The diversification of primitive fish, such as pterospidomorphs, marks a gradual conquest of varied aquatic habitats. Thanks to their dermal bone plates, they occupied environments ranging from warm, shallow waters to deeper, rougher areas. This protection gave them a clear advantage over non-armored forms. With the rise of marine predators, including giant arthropods, their hardened carapace became an essential asset for survival. The Ordovician Great Biodiversification Event complicated marine life, from plankton to top predators. The pterospidomorphs and eurypterids are major examples of this evolution. Various brachiopods, bryozoans, and cephalopod mollusks also contributed to enriching biodiversity, each with specific armors, modes of movement, and habitats. These groups coexisted sometimes peacefully, sometimes in intense rivalry, illustrating the increasing complexity of marine ecosystems. The first mossy soils linked to cryptospores were a crucial step, providing damp environments conducive to the emergence of terrestrial arthropods, such as primitive scorpions and myriapods. Although the massive animal conquest of the continents was still far off in the Ordovician, this period marks the beginning of the transition. Marine life diversifies, while terrestrial life takes hold with plants and biofilms. This progressive greening would profoundly influence the atmosphere, climate, and geochemical cycles. Specialized bioerosion in the Ordovician, illustrated by Triponites borings, shows an effective strategy, boring into skeletons and shells for shelter or nutrition. This tactic circumvents passive defenses, making thick shells vulnerable. These opportunistic organisms transform the habitat of other species into refuge, demonstrating the adaptability of living beings. In response, prey improve their defenses, reducing internal space or strengthening the shell. These fossil holes are evidence of intense competition and increasing complexity of marine ecosystems. The innovations of the Ordovician, explosion of marine diversity, armor and locomotion of fish and eurypterids, first terrestrial plants, and specialized bioerosion illustrate the vitality of this key period. These advances shaped ecosystems and laid the groundwork for future evolution. Fossil layers show that the Ordovician marked an irreversible rise in biological complexity, from coastal areas to ocean depths. This crucial chapter heralds a world where predation, defense, mobility, and land colonization will redefine life for millions of years. During the Ordovician, the Earth transitioned from a super greenhouse effect to a glacial climate or icehouse characterized by polar ice caps. This change is linked to the shift of Gondwana towards the South Pole, encouraging ice formation and global cooling. The decrease in greenhouse gases, such as carbon dioxide, also led to a drop in temperatures. Tropical waters cooled down, and significant glacial expanses emerged, impacting marine communities and oceanic oxygenation. Initially, a super greenhouse effect elevated temperatures and favored marine productivity with nutrient-rich seabeds. Then, as Gondwana approached the South Pole, glaciers formed, modifying ocean circulation and increasing contrasts between cold and temperate waters. Between 2020 and 2024, studies showed that this reorganization stratified the oceans, limiting vertical mixing and creating anoxic zones where only specialized bacteria survive. Anoxia in deep waters reveals a decoupling between the ocean's surface and bottom. Photosynthesis at the surface maintains the oxygen necessary for diverse marine life, while the absence of deep mixing deprives lower layers of oxygen. This creates dead zones inhospitable to most marine animals. Sediments accumulate undecomposed organic matter, providing researchers with clues on climate evolution and its impact on marine fauna. This pattern is confirmed by recent studies. During the Ordovician, a significant flux of extraterrestrial debris, notably stony meteorites called L-type chondrites, pelted the Earth. These dust particles enriched the oceans with chromium, possibly stimulating phytoplankton growth. However, their climatic impact remains secondary to the migration of Gondwana, the reduction of carbon dioxide, and the formation of ice. This event illustrates the constant connection between Earth and cosmic phenomena in the solar system. Chrome analyses in deep sediments allow us to assess the flux of extraterrestrial debris over several million years related to collisions in the asteroid belt. However, these events alone do not explain the major climate transition at the end of the Ordovician. Evidence primarily shows a cooling caused by a decrease in carbon dioxide and the formation of large polar ice caps. The configuration of continents and ocean-atmosphere interactions play a central role, while cosmic dust is a secondary factor. The accumulation of ice at the South Pole alters sea levels and the arrangement of sedimentary basins. The retreat of inland seas exposes rocks subjected to erosion, trapping carbon dioxide and reducing its concentration in the atmosphere. This process further cools the planet, creating a positive feedback where the spread of ice enhances global cooling. Isotopic markers confirm a major glacial phase during the Ordovician, with immense ice sheets transforming global ecosystems. Ocean circulation reorganizes under the influence of cold polar waters plunging, but the rapid spread of ice disrupts this flow, creating anoxic deep zones. Between 2022 and 2024, studies revealed that these oxygen-poor regions see the disappearance of many species. Survivors adapt or migrate to oxygen-rich waters. This stratification also influences nutrient distribution and marine productivity. Sediments preserve geochemical traces of these episodes. During Earth's cooling, meteoritic flux, notably from L-type chondrites, supplied metals nourishing certain microorganisms. Yet, its impact remains secondary to internal climate forces. Asteroid collisions created a prolonged rain of tiny debris enriching sediments in chrome. However, the main environmental turning point corresponds to the formation of large ice caps. Meteorite falls are not directly linked to cooling, dominated by the position of continents and the decline of carbon dioxide. Scientists trace the Ordovician's history using various indicators: stable isotopes, mineral composition, marine fossils, and chemical anomalies. Drilling reveals rock layers recording past fluctuations. Isotopes provide information on temperature and organic matter burial. Fossils show species reactions to climate changes, while chrome indicates meteorite passages. Together, these data illustrate a once hot Earth that cooled, influenced by a continuous flow of extraterrestrial debris. The Ordovician demonstrates the interaction of multiple forces transforming Earth. The super-greenhouse effect gave way to marked cooling with thick ice caps and retreating seas. Concurrently, L-type chondrites deposited chrome in sediments, but the drift of continents towards higher latitudes and the decline of greenhouse gases remain the primary drivers, leading to a colder planet with partially anoxic oceans. These related phenomena highlight the complexity of climate and oceanic circulation, reinforced by cosmic influences. We explore 5 remarkable paleontological sites. The Lagerstätten, known for their exceptional preservation of soft organisms. These deposits, of German origin, preserve not only shells and skeletons, but also fragile tissues that usually disappear. They offer unique windows into ancient life, constituting precious time capsules that enrich our understanding of biodiversity evolution. We dive chronologically into these major Ordovician sites, a period ranging from approximately 485 to 443 million years ago. These locations reveal fascinating organisms, ranging from primitive marine arthropods to jawless fish, as well as other mysterious life forms. Their study has required patience and precision to identify and reconstruct them. Our role is to make this journey through time accessible to everyone, even novices. We will explore in detail Fezuata, Cabriere, Winneshiek, Beecher's Trilobite, and Soom Shale, explaining their conservation, the ancient environment of species, and their importance to evolution. These sites bear witness to particular geological, climatic, and chemical conditions that have preserved these fossils for millions of years, a captivating journey into an ancient and mysterious oceanic world. Our first stop is the Fezuata Formation in southeast Morocco. Millions of years ago, this location near the equator enjoyed a subtropical climate and shallow seas teeming with astonishing fauna. Clay sediments slowly covered these organisms, compacting to form a mineral envelope that has preserved them to this day. Fezuata is notable for the preservation of rare soft-bodied organisms, including enormous marine arthropods like Egyrocassus, a peaceful giant filtering plankton. The site has also revealed echinoderms with unusual shapes and species, similar to those of the famous Burgess Shale fauna in Canada. Fezuata extends this Paleozoic legacy, linking the Cambrian era to more recent times. The fossilization at Fezuata is remarkable. Fine clay deposits preserve precise details, sometimes in phosphorus-rich or iron-rich films. One can distinguish segments, fine gills, and fragile internal structures. These fossils provide a detailed view of Ordovician life. Careful excavations, often with chisels, reveal marine life from about 480 million years ago, shedding light on the evolution of ecosystems between the Cambrian and Ordovician. We head to the south of France, to the Montagne Noire, near Cabriere. Now calm, this place was covered by a cold sea about 470 million years ago, located at high latitude or influenced by polar currents. At that time, carbon dioxide emissions varied, and the global climate experienced intense warming, known as super greenhouse. Yet, some seas remained cool due to the drift of continents and the geographical position of France. The Cabriere site, known as Cabriere's Biota, presents an exceptional fossil assemblage where soft-bodied organisms are preserved thanks to iron-rich compounds, sometimes giving a unique coloration to the fossils. This preservation allows us to observe sponges, lobopods, and trilobites without their usual mineralization. More than 400 specimens have been discovered, offering a valuable glimpse into a polar or subpolar marine ecosystem. Excavations at Cabriere continue, with discoveries to come that will clarify the beginnings of the Great Ordovician Biodiversification Event, a remarkable period of marine life expansion. The exceptional preservation of fossils reveals a chemically rich environment in iron, which favored the rapid formation of protective films around soft organisms, preventing their decomposition. Thus, delicate creatures have been preserved almost intact for tens of millions of years. In the American Midwest, at Winneshiek, an exceptional site dating from about 400 to 67 million years ago, a shallow marine region transformed into an underwater impact crater. A space object struck the Earth, forming a circular depression. The debris from this impact enabled the remarkable preservation of organisms, especially in the crater's ring, offering a unique glimpse into ancient marine life. The lacustrine impact fauna of Winneshiek comes from a basin formed after a meteoritic impact, where water stagnated in a closed depression. Rapid sedimentation covered the dead organisms, slowing their decomposition and promoting their fossilization. This site contains soft-bodied arthropods, ancestors of eurypterids, primitive fish, and various invertebrates. Unlike usual devastating impacts, Winneshiek offers exceptional conservation of post-collision life. The study of the Winneshiek site sheds light on mid-Ordovician marine and lacustrine fauna, showing how life recovered and thrived around ancient craters. 3D tomography allows researchers to better visualize the internal structures of fossils and analyze the detailed anatomy of previously little-known species. This site is essential for understanding the influence of extraterrestrial events on the evolution of biodiversity during this period. Our journey takes us to the state of New York, to Beecher's Trilobite bed, famous since the late 19th century. This unique site preserves trilobites, iconic marine arthropods from the Paleozoic, in 3D. While other deposits retain only their mineralized shells, Beecher's Trilobite also shows soft parts, notably the digestive system and sometimes the appendages, offering a rare and valuable insight into their anatomy. The exceptional preservation of Beecher's trilobite fossils is explained by pyritization. This mineral of iron and sulfur, also called fool's gold, formed thanks to bacteria that consumed the decaying tissues and precipitated compounds around the soft parts. Pyrite thus recreated the internal anatomy in relief. This process requires a precise chemical balance, with sufficient iron, little oxygen, and rapid burial of the fossils. The trilobites of Beecher's trilobite are key Ordovician arthropods, witnesses to an important stage of marine evolution. Adapted to seafloors subject to climatic and marine variations, their fossils reveal not only their morphology, but also their behavior. The study of appendages shows various locomotion strategies, phases of burrowing into sediments, and possible feeding modes, offering a detailed glimpse into their way of life. Thanks to microtomography, a non-destructive scanning technique, previously invisible details, like sensory filaments on the appendages, have been discovered. These advances make this site an essential place for studying Ordovician life and the animal adaptations to environmental changes. They also reveal the relationship between biological structures and rare geochemical conditions that allowed the exceptional preservation of these fossils. Our last stop is in South Africa, at the Soom Shale Formation, about 445 million years old. This period corresponds to a marked cooling and the expansion of ice in the southern hemisphere. Unlike the warm seas of Fezuata or Cabriere, the South African waters were colder, often with poor or low oxygen bottoms. The preservation at Soom Shale is exceptional due to phosphate collagen mummification. The soft parts, usually fragile, were impregnated with phosphates while retaining traces of collagen, an essential protein of tissues. This very faithful mineralization allowed the discovery of varied fossils, including pycnogonids or sea spiders, and primitive cartilaginous sharks, testifying to the Ordovician marine diversity of this region. This deposit contains, besides pycnogonids and chondrichthyans, rare species that illuminate the environmental upheavals at the end of the Ordovician. Chemical analysis reveals episodes of anoxia favoring rapid fossilization before bacterial decomposition. The study of fossil orientation and fossilized tissues helps to understand sedimentation. These conditions are similar to those of shallow basins affected by glacial influences, confirming the progressive cooling of the Earth at this time. The Soom Shale reveals faunal diversity and documents significant climatic transformations, marked by the development of ice sheets in the southern hemisphere. The 5 Lagerstätten offer an exceptional glimpse of global Ordovician fauna. From North Africa to Europe and North America, each site provides keys to the preservation of soft tissues, ecosystem evolution, and geological conditions that allowed their preservation. Thanks to rapid burial, pyritization, and phosphatic mineralization, ancient life reveals its mysteries to us, enriching our understanding of marine history in the Ordovician. Between 2024 and 2025, major scientific advances enriched our understanding of the Ordovician. These discoveries, published in various journals, illuminate key aspects of life, climate, and ancient environments. Although complex for non-specialists, they provide essential elements for reconstructing Earth's evolution. This section will present 5 recent discoveries, clearly explaining their scope and associated scientific concepts. The Taichut section at Fezuwada reveals a continuous stratigraphy dating back about 480 million years, with a varied marine fauna, including ancient arthropods and atypical echinoderms. In 2224, a study in Nature highlights a unique paleoflora composed of primitive plants akin to bryophytes, colonizing the humid shores. These plants formed thin mats, stabilizing sediments, marking a key step in the gradual transition from marine to terrestrial life, preparing for the gradual conquest of emerging lands. The Cabrières biota in the Montagne Noire in France reveals an exceptional polar ecosystem about 470 million years old. Located at a high latitude at the time due to continental drift, the site exhibits a rare iron-based conservation, mineralizing the soft parts of organisms. It allows detailed study of sponges, soft arthropods, and lobopodians, illuminating the evolutionary links between arthropods and legged worms. This discovery shows that the Ordovician was not limited to the tropics and offers insights into adaptation to cold climates. The discovery of the neurocranium of Aeroptychius, a primitive vertebrate from the Paleozoic, was made possible through 3D tomography, revealed in Nature in 2023. This cartilaginous skull, rarely fossilized, is the oldest articulated brain identified. It shows that complex brain structures existed about 458 million years ago. The precise reconstruction sheds light on the sensory capabilities of the fish. This major advancement illustrates the rapid neurological evolution in early vertebrates and their early complexity. Fourth discovery: uranium lead dating of zircons taken from the Slate Islands, a site associated with the Ordovician meteorite event known as OME. In 2024, a detailed analysis of these minerals refined the date of the impact that occurred during the Ordovician. Zircons, very stable minerals, contain uranium which slowly decays into lead. By measuring their proportions, scientists read a natural clock that reveals the age of the crystal formation. This very precise method offers a refined temporal calibration of geological events. This new dating confirms that the increased meteorite flux at this time, linked to the fragmentation of a large chondritic asteroid, was a key moment of the Ordovician. It also provides an essential marker for studying the cosmic impact on the marine ecosystems of the time. Some researchers suggest that the debris enriched marine basins with nutrients, promoting biodiversity, while others believe that dust fallout may have temporarily altered the climate. This dating is part of a broader project aimed at precisely linking each paleontological event to its geological context. The fifth discovery concerns the re-evaluation of the Hirnantian carbon isotope excursion, or HICE, studied in 2024. This research examines the connection between the massive glaciation at the end of the Ordovician and the variations in the carbon cycle recorded in sediments. The carbon cycle refers to the constant exchanges between the atmosphere, oceans, biosphere, and rocks. An isotopic excursion indicates an unusual variation of a carbon isotope, signaling a climatic or ecological upheaval. The Hirnantian carbon isotope excursion during the late Ordovician is one of the most pronounced of the Paleozoic. It coincides with a major glaciation that caused a drop in sea level and significant pressure on marine life. A recent study revealed that this isotopic fluctuation occurred in less than 100,000 years, a very short time span in geological terms. This discovery helps in understanding the rapidity of climate changes and their impact on organisms. During Earth's cooling, vast polar ice sheets accumulate fresh water, leading to a worldwide drop in sea level. This evolution modifies biological communities, favoring adaptable species. Additionally, carbon fixation by organisms and terrestrial plant variations influence the isotopic footprint. The study of these links helps in understanding the interactions between climate, carbon cycle, and extinctions. The recent re-evaluation of the Hirnantian isotopic excursion improves the dating and understanding of these phenomena. Advances in the Ordovician have been made possible thanks to modern tools like 3D tomography and uranium lead dating. The dialogue between earth sciences and life sciences is crucial to reconstructing this ancient history. Without this multidisciplinary approach, it would be impossible to connect biological innovations, carbon cycle variations, and cosmic events. This richness makes the Ordovician a fascinating period of rapid evolution and major climatic upheavals. These studies offer precise chronological milestones, allowing us to pinpoint the appearance of animals, the arrival of land plants, and the succession of celestial events related to meteoritic impacts. A shift of a few thousand years can change our understanding of the causes of extinctions or isotopic excursions. Each new piece of data enriches and adjusts our understanding of the Ordovician and its upheavals. These international efforts illustrate a collective endeavor to understand life hundreds of millions of years ago and how a dynamic Earth shaped biodiversity. The stakes go beyond paleontology. They concern the speed of climate changes, the resilience or vulnerability of ecosystems in the face of sudden events, and their long-term adaptation, which are crucial questions today. Even though the Ordovician biosphere differs from ours, some essential mechanisms, the carbon cycle, thermal sensitivity, responses to sea level drops, remain relevant in climate debates. Recent investigations focus on coastal and subpolar margins. In Cambrian, the remains of polar species reveal cold adaptations as early as the Ordovician. In Taishut, the discovery of a paleoflora provides information on the colonization of shores. The climate of the Ordovician, initially extremely hot, evolves towards a glacial period at the end of the period. Researchers are trying to understand how these changes affected local ecosystems, using the stratigraphic continuity of Taishut to observe modifications in fauna and flora. The recent discoveries of 2024 and 2025 reveal a renewal in Ordovician research. The 3D tomography of Arapticius reveals detailed information on internal anatomy and neurological evolution. Uranium-lead dating of zircons from the Slate Islands refines the chronology of a major meteoritic impact. The Taichout section in Morocco offers new insights into marine and terrestrial life, while the Cabriere biota sheds light on a polar ecosystem. The reassessment of the Hirnantian carbon isotope excursion shows the rapidity of climatic changes. The common denominator of these recent discoveries is chronological precision and multidisciplinary analysis. Modern science allows us to decipher the signals of extinct living beings, sea level variations, meteorites, and climate. Each study contributes to reconstructing the history of life on Earth, whether it involves primitive fish, ancient minerals, or tropical vegetation of the Ordovician. Although much remains to be discovered, these findings already illustrate the scientific dynamism surrounding the Ordovician. The Ordovician is far more than just a simple explosion of biodiversity or glaciations. It is an era of transitions, anatomical innovations, and environmental upheavals in a surprising geological context. Thanks to recent studies, our understanding of this period continues to grow. Paleontology enthusiasts and all the curious can appreciate these advances as they bring us closer to a more precise vision of life's evolution on Earth before subsequent periods.